All right, guys. So obviously at this point, we have just finished up that activity introducing you to the idea of what's called the Koch snowflake. So what we're going to do now is we're going to go ahead and look a little bit about the history, but talk more about some of the key features of this snowflake and kind of some of the cool stuff about it. So that being said, the history of it, first of all, the actual snowflake itself is named after a Swedish mathematician by the name Helga von Koch. And they were alive from 1870 to 1954. Pretty recent, really, as far as the history of math goes. There hasn't been a lot of new developments within the last 100 or so years. This is actually a pretty recent kind of thing that we're looking at. It's our first example of what you call a geometric fractal. So that's going to be kind of our key thing that we're going to be studying throughout this chapter is what are called geometric fractals. And so this is our first one. We'll continue to look at some other ones as well, like the Sierpinski gasket, as well as the Mandelbrot set. So some different ones that we will look at in upcoming sections. Now, like those other geometric fractals that we're getting ready to study, the Koch snowflake was created by what's called a recursive process. And so basically a recursive process is just a process which is just applied repeatedly in the same kind of loop. In other words, the output at one step becomes input at the next, and you just continue to do that over and over again. Just like we continue to create this shape kind of over and over again. Now I'm going to go ahead and skip over these slides. These are obviously talking you through how to create the snowflake, which is what we did in class together. But if you ever need to go back and remember how to create the snowflake, those would be some good slides to go back and take a look at. Now, what's kind of interesting about this is that obviously it creates a new snowflake at each step, but as you continue to create this, especially when you get to a point where your snowflake looks something like this, it really becomes almost impossible to notice a difference from step to step at this point. Like even if you were to zoom in really far and create all those extra little crinkles that we call them on each of the sides and then zoom back out, you probably wouldn't even notice the difference between a snowflake at this step and one at the next step. And so that's going to be kind of where we will notice the actual Koch snowflake itself, which is, again, kind of the theoretical idea of if you continue to create it over and over again, eventually you'll get to a point where it's going to basically have to be that. It's going to become what's called visually stable. And again, that just means that the naked eye is not going to notice any difference between one snowflake and what it looks like at the next step. Now, one kind of nice part about these recursive processes that we're going to use when we create these different geometric fractals is that they're pretty simple as far as the definition and the steps go. Obviously, the Koch snowflake is going to be and it is a very complicated shape, but obviously there's really only two steps that you really have to do. And really it's just a replacement rule. So here's what that is. You start with a shaded equilateral triangle. That's going to be the seed of your graph. And then you're just using this replacement rule to replace every boundary with a crinkled version. And obviously in the Koch snowflake, that meant taking a straight line and creating a new equilateral triangle coming out of it. Now, if we only think about the boundary of the snowflake and not about the interior of it, we get a curve which is called either the Koch curve or the snowflake curve. So if, instead of talking about the kind of shaded region, everything inside, but only talking about the boundary of it, we call it the Koch curve or the snowflake curve. Now, if you just pick any part of it and zoom in, surprisingly or not, I don't know if it surprises you, but there's really nothing different. It's going to look the exact same no matter how far you zoom in. In fact, on this next slide, you'll be able to see that in practice. So if you have your original Koch curve right here on the left, if you zoom in on this piece right here, you get this picture right here, which you can see looks the exact same as what it did over here, just zoomed in. And again, if you were to zoom in on a piece of that part of the curve, you end up with another picture, which again looks the exact same as what it did. That's that recursive part. So really, no matter where you pick this graph, it's going to look the same as itself as you continue to zoom in on it. That idea is what is called self-similarity, is that when you continue to zoom in on one part of this uh, graph and one part of this curve, it's going to continue to look like itself. That's that self-similarity idea. Now, there are basically three important properties that we're going to talk about in relation to self-similarity. And this is going to be stuff that we continue to talk about for the other fractals as well. So those three properties, the first is that it is infinite. And so no matter how many times you magnify the curve itself, it's always going to look the same. So that's what we call infinite self-similarity. Number two, it's universal. So the same self-similarity occurs every part of the Koch curve. So no matter where you look at on the curve, it's going to look the exact same, and that's going to be no matter where you pick, whether it's at the very top of it, maybe up here, or whether you pick this part like they did in the slides, or this part down here, or even this part right here. No matter where you pick, it's going to continue to look the same as what you would see on the entire curve. The third is going to be that it's exact. So you see the exact same image at every level of magnification. So again, as we continue to zoom in on that one part of the Koch curve, it continued to look the exact same. It didn't start changing all of a sudden. It didn't have a new pattern all of a sudden. It continued to look the exact same as we continued to zoom in on one particular part. Now, these are all kind of the ideal scenarios. Not everything is going to have infinite, universal, and exact self-similarity. So we'll talk a little bit more about approximate similarities, which is the opposite of exact. So you have exact and approximate. You also have both universal and local self-similarity. So these are kind of the opposites of the ideal form. And instead of infinite, we obviously have finite self-similarity as well. So again, these are kind of your three opposites or three kind of imperfections of each of these, which again, we would kind of consider to be the best possible self-similarities. Okay, now, obviously, that's cool, but where does this apply in the real world? And that is a big part of this class is not only seeing some of the cool stuff of math, but where do you actually see this in the real world? And one good example of this is in cauliflower. If you've ever looked at a head of cauliflower and then looked at its individual kind of pieces that come off of that, it actually, when you take a piece of cauliflower off of the head, that one piece of cauliflower looks a lot like the rest of the head of cauliflower. And actually, as you get closer and closer, and if you were to zoom in, maybe under a magnifying glass or something like that, you can actually see that it does look self-similar. Now, obviously, in nature, it's not going to be perfect. So in nature, your self-similarity is not going to be infinite, not going to be exact. So instead, this would be that example of where we talk about an approximate self-similarity as opposed to exact. In fact, just to illustrate that point, here's what that looks like in terms of the cauliflower. So if you have your entire head of cauliflower right here, as you zoom in on one particular part, you get an image like this. And as you zoom in on a part of it, you get an image like this. So you can see that even in nature, and in this instance, for this cauliflower, you do have a lot of those same ideas that we saw in the Koch snowflake. In fact, I would encourage you to look in the textbook as well for section 12.1. They've got a lot of cool pictures in there showing a lot of these types of ideas with self-similarity and showing where those are in nature. Now, one interesting fact about the Koch snowflake is how the perimeter and area relate to each other. And so what's kind of interesting is that it's actually got a relatively small area. And in fact, there's a simple calculation that you can do in order to find that area. Whereas the perimeter is going to be actually infinite. If you think about it, every time you create a notch, you add a little bit to the perimeter. So it's kind of something that almost defies your logic or your common sense. But it's kind of easier to see as we consider it within a circle. So we're going to look at when you circumscribe this triangle in a circle, kind of how that can help you to visualize that the area will be fixed, but that the perimeter keeps growing. So keep in mind this, and we did this a little bit with the activity in class, but anytime you replaced a side by 4 more sides that were 1/3 as long, that gave you a new perimeter that was 4/3 the perimeter at the preceding step. So as you continue to go, your perimeter continues to grow and actually grows pretty quickly. Now, after continuing to do this an infinite number of times, it only makes sense that the perimeter also is going to have to be infinite. But the area is not. In fact, here's what I was mentioning before. When you consider it, when you have a circumscribed triangle, notice that it's never going to actually get outside of the bounds of that circle. No matter how many times you continue to add the triangles to it, notice that the area is going to be kind of fixed within this particular circle. In fact, we can actually be pretty specific. The area of your Koch snowflake is going to be 8/5 or about 1.6 times the area of the seed triangle. So if you have a way to find the area of that triangle, then you can actually find the area for the Koch snowflake, because again, that becomes a fixed value as opposed to becoming infinite like the perimeter. Something that you don't necessarily always kind of think about with normal shapes and normal figures. We typically think that as the perimeter increases, so does the area, and vice versa. And that's actually not the case with this fractal geometry. Now, obviously, having a very large boundary packed with a small area is an important characteristic of a lot of shapes in nature as well. Obviously, long boundaries can improve functionality, small volumes keep energy costs down, and so on. One example of that is actually the vascular system, if you think about it. Obviously, the veins and arteries in your body are very small, but create a very large length and volume, which obviously is a necessity. In fact, it's kind of interesting if you were to lay them end to end, all the veins, arteries, capillaries of a single human would be more than 40,000 miles long. So a very, very long perimeter, I guess, if you want to think about it. But they really don't take up much area in your body compared to a lot of the other things. So kind of an interesting thing that you would see there. So this last slide really just kind of summarizes a lot of the key properties. I would make sure that you've got these copied down somewhere in your notes. The fact that it has both exact and universal self-similarity is a big one. That's not going to be necessarily the case with the other fractals that we'll look at in later sections. It also has an infinite perimeter, which also is just kind of interesting. Again, won't always be the case. And finally, its area is an exact value. It is 1.6 multiplied by the area of the seed triangle. So although the perimeter is infinite, the area is actually a fixed number. All right, guys, so that is it for us in this Koch snowflake. In our next section, we're going to talk about what's called the Sierpinski gasket. We'll have a similar kind of thing to do in order to construct it, a kind of fun way to do that as an activity at the start of next class period. And then we'll get into some more of the details like we did with the Koch snowflake today. Until next time, have a good rest of your day.